how far can tested physics take us toward the universe portrayed in Interstellar before informed speculation must take over?
Yeah, that's really the ultimate tension at the heart of this material. I mean, the story is this fascinating hybrid
Right.
because on one hand, you have experimentally supported general relativity and observed astrophysical black holes.
The real stuff.
Exactly, the real stuff. But then it takes those concepts and merges them with model-dependent extrapolations, and eventually, it crosses into entirely unconfirmed ideas.
Like the traversable wormholes or higher dimensional intervention.
Yeah, and communication with the past, things like that.
Right, because when human survival requires breaking the known limits of physics, you have to navigate that exact boundary.
Mm-hmm.
And to understand the sources we're analyzing today, we kind of have to follow that logical progression of survival. Like if humanity has to leave, we first have to reckon with the fabric of space-time itself.
Yeah, and gravitational time dilation.
Exactly. And from there, we're forced to deal with the brutal mechanics of rotating black holes, how a massive object like Gargantua actually dictates its local environment.
Right, and we'll look at the reality of those extreme planetary orbits.
Yeah, and the visualization of the unseeable, the mechanics of wormholes, the sheer vastness of interstellar travel, gravitational waves, and then finally, the absolute unresolved frontier of quantum gravity.
It's a progression from what we can rigidly measure to what we can only, mathematically imagine.
Yeah, well said. So our mission in this deep dive into the Cosmora HQ overview of Kip Thorne as the science of Interstellar is really to separate mathematical possibility from technological reality.
Yes.
So before a spacecraft can even approach a black hole, we have to understand the universe it sits in. We have to understand that space and time are this single dynamical geometry. So let's unpack this. Because a central problem in this story is time. Astronauts spend a few hours on a planet, and they age normally, but decades pass for the people they left behind. So mechanically, how does gravity actually reach into a mechanical watch or a biological cell and slow it down?
Well, it doesn't.
It doesn't.
No, it doesn't reach into the watch or the cell at all.
Yeah.
The underlying concept here is something called proper time.
Okay.
So proper time is local and it's operational. It is the time recorded by a moving, well-functioning clock right there beside the observer. So the watch isn't broken, right?
Right.
And the biological cell isn't functioning in slow motion either. The universe is just structured such that elapsed time is entirely dependent on the path you take through space-time.
So we have to basically stop thinking of time as this universal ticking clock in the background of the cosmos.
Precisely. A good way to think about it is like an odometer in a car.
Okay.
Right? So if you and I drive from point A to point B, but I take a straight highway and you take a winding mountain road, our odometers will show totally different mileage.
Yeah, obviously.
Right. But neither odometer is broken. We just traversed different distances through space. Space-time works similarly. Gravity is the literal curvature of that geometry.
Right.
So because mass curves space-time, a clock deeper in a gravitational field is traversing a different geometric path than a clock further away.
Oh, wow.
And therefore, they accumulate different amounts of elapsed proper time. So gravitational time dilation is a fully theoretical consequence of relativity, but it's one we've actually proven here on Earth.
Which means the time they are experiencing is completely real.
Yes.
And that actually brings up a major misconception we need to clear up regarding the event horizon. Because a common trope is that if a traveler falls into a black hole, time just universally stops.
Yeah, that is a severe misunderstanding of relativity, mostly because it ignores who is doing the observing. Time does not universally stop at an event horizon.
It doesn't.
No. If you are the traveler falling in, you experience perfectly normal, local, proper time. You could check your pulse, look at your watch, and everything would feel totally continuous.
But the people watching you fall wouldn't see that.
Right, they wouldn't. If I'm a distant observer safely outside the gravity well, the light signals you emit as you fall have to climb out of that extreme gravitational curvature,
Wow.
and that requires energy. So as the light loses energy climbing out, its wavelength stretches.
I see.
So to me, your image appears to slow down, freeze at the horizon, and heavily redshift. It turns red, then infrared, then radio, until you just fade entirely. Your time hasn't stopped. My view of your time has been fundamentally distorted by the geometry between us.
Wow, okay. That sets us up perfectly for the anchor of this entire system, which is Gargantua. To get the extreme time dilation required by the story without immediately falling into singularity, you need a very specific environment.
You do.
You need a Kerr black hole, right? A rotating black hole. Now, anyone who follows astrophysics knows the old cosmic vacuum cleaner myth is false.
Yeah.
They aren't just indiscriminately sucking up everything in the universe.
Wait, they definitely don't suck.
Right, but I want to look at the mechanics of why things actually fall in versus stay in orbit.
Yeah.
If you're in a spacecraft orbiting close to a massive body, shouldn't centrifugal force keep you safe?
Well, in Newtonian physics, yes. In classical physics, you can orbit at almost any distance as long as you're traveling fast enough sideways.
Right.
But a black hole is an observed astrophysical object that drastically warps those rules. In general relativity, gravity gets stronger much faster as you get close to the mass than Newton's laws predict.
Okay.
So this creates something called the innermost stable circular orbit, or the ISCO.
The ISCO. So that's like the mathematical point of no return for an orbit.
Exactly. Below the ISCO, the curvature of space-time is so severe that circular paths simply cease to exist.
Oh, wow.
Yeah, no matter how fast you travel sideways, centrifugal force cannot overcome the geometry funneling you inward.
So you just fall.
Yeah. The only way to avoid falling is to point your engines directly away from the black hole and fire them continuously with massive thrust, which is, totally unsustainable.
Right. But Gargantua isn't static. It's spinning at a significant fraction of the speed of light.
Yes, and that rotation brings in the Kerr solution. Because Gargantua is spinning, it produces a profound effect called frame dragging.
Frame dragging?
Yeah, it doesn't just curve space-time, it actively twists the local inertial frames around it.
So it's like taking a wooden spoon and aggressively stirring a thick bowl of syrup. The syrup itself drags whatever is suspended in it, just spinning it around the center.
Right.
Except here, it's not syrup. It is the fundamental fabric of reality being pulled along.
That analogy works really well because it emphasizes that you are being moved by the medium itself. If you're near a rapidly spinning black hole, you physically cannot stand still relative to the distant stars. Space-time is sweeping you along.
Yeah.
But we also have to clarify the geometry of the black hole itself here, because the event horizon is purely a causal boundary.
Okay, what does that mean exactly?
It is a threshold where the escape velocity exceeds the speed of light. So future directed signals cannot escape to the outside world. It is not a solid physical shell you crash into. And it is entirely distinct from the singularity itself, which lies deep inside the horizon where the curvature becomes infinite.
Got it. So here's where it gets really interesting, because the math for that Kerr metric dictates that if you are in a prograde orbit, meaning you're orbiting in the same direction that space-time is being dragged,
Right.
that innermost stable circular orbit gets pushed much closer to the event horizon, close enough to experience that massive time dilation. But mathematical permission doesn't equal a safe vacation spot, right?
No, definitely not.
How does a planet even physically survive there without being torn to shreds?
Well, the idea of a planet physically surviving that close to a supermassive black hole relies on highly model-dependent extrapolations.
Okay.
The primary hazard is extreme tidal gravity. Tidal gravity is just the difference in gravitational pull across an object.
Like how the moon pulls on Earth's oceans.
Exactly. But here, the pull on the side of the planet facing the black hole is drastically stronger than on the far side, so it stretches and compresses the planet.
Spaghettification.
Exactly. But this is where the mass of Gargantua is crucial. A stellar mass black hole has an incredibly steep tidal gradient near its horizon. It would shred a planet or a person instantly.
Yikes.
Yeah. But a supermassive black hole, like Gargantua, is millions of times more massive, which means its event horizon is much further away from the singularity.
Oh, I see.
So the change in gravity over the diameter of a planet is much gentler at that distance. So mathematically, the planet can physically exist without being ripped apart.
Okay, but existing isn't surviving. Because even if the planet holds together, you still have to contend with the accretion disk, that superheated gas spiraling around the black hole.
Oh, yeah, the accretion disk is a completely lethal environment.
I would imagine.
As gas spirals inward, friction heats it to millions of degrees, pumping out intense radiation, X-rays, gamma rays, intense heat. A planet orbiting in or near that disk would be subjected to constant sterilization by hard radiation, not to mention orbital perturbations and physical impacts from debris.
Which really highlights how demanding the assumptions for habitability actually are. I mean, we often hear that finding liquid water means a planet is a candidate for life.
Right, but liquid water is just a baseline. Habitability requires profound stability. You need an energy balance that can be maintained over geological timescales. You need atmospheric chemistry and stability. A mathematically stable orbit in a Kerr metric doesn't protect a fragile ecosystem from the realities of high-energy astrophysics.
So if the environment around Gargantua is so chaotic and deadly, how did the scientific and visual effects teams manage to produce that incredibly coherent, iconic image of the glowing ring? Like, we need to look at how we visualize the unseeable here.
Right.
So is this just artists painting a pretty picture, or is this what a camera would actually see?
It's an interpretive, scientifically informed visualization. It's not a photograph or a raw observation. To create it, the visual effects team used numerical ray tracing.
Okay, what is that?
They computationally calculated the exact paths of millions of individual light rays as they traveled through the twisted spacetime of the Kerr metric.
Oh, wow.
Yeah, tracking how the black hole's mass bent those rays before they reached a virtual camera.
And the result of that is gravitational lensing, right? Which produces this fascinating optical illusion because the black hole is surrounded by a flat equatorial disk of glowing gas.
Right.
But because the gravity is so intense, it warps the light coming from the back of the disk. It bends that light over the top and under the bottom of the black hole shadow.
Exactly. It turns the curvature of space into a massive, distorted lens. However, to make it a recognizable cinematic image, the teams had to make specific presentation decisions regarding the physics.
Like what?
Well, in reality, the incredible orbital speeds of the gas in that accretion disk would cause massive Doppler shifts.
Doppler beaming, right. The light moving towards you gets compressed and amplified.
Yes, the side of the disk spinning toward the camera at a fraction of the speed of light would be blindingly bright and blue shifted. Those photons are packed closer together and pushed to higher energies.
And the other side.
Conversely, the side spinning away would be incredibly dim and redshifted. Additionally, you have gravitational redshift dimming the light closest to the horizon, where light loses energy just trying to escape the gravity well.
Okay, so if they had rendered a completely raw, physically accurate image, we wouldn't have seen that majestic halo. We would have seen this lopsided, blindingly bright crescent on one side and almost nothing on the other.
Pretty much. So they made an interpretive choice to dial down the Doppler beaming so the audience could actually see the complex geometry of the spacetime curvature.
That makes sense.
That is the essence of an interpretive rendering. It sacrifices one physical reality, the extreme brightness variation, to effectively communicate another physical reality, which is the gravitational lensing.
Got it. So what does this all mean for actually reaching a system like this? Because the distances in astrophysics are a fundamental barrier. To even reach Gargantua, the story requires a massive shortcut, a wormhole situated near Saturn.
Right.
We've established that black holes are observed. Are wormholes just a different flavor of a black hole?
No, and it is vital to draw a hard line here regarding evidence. Black holes are observed astrophysical objects.
Okay.
We have detected their gravitational pull on stars, we've captured their shadows with the Event Horizon Telescope, and measured their collisions. Traversable wormholes, on the other hand, are completely speculative. They are unobserved theoretical constructions.
But the mathematics of general relativity permit them, don't they? The equations allow for two separate regions of spacetime to be connected by a throat or a bridge.
They exist in the math, sure. But keeping a wormhole open so a macroscopic object could travel through it requires what physicists call exotic stress energy.
Okay, exotic in what way?
Well, gravity dictates that mass wants to collapse. So the natural tendency of a wormhole throat is to instantly pinch off and crush anything inside it.
Right.
To prevent that, you need a material with anti-gravitational pressure, effectively negative energy. You need it to act as scaffolding and hold the throat open.
Okay, I have to push back on that. Because energy is just energy. How can energy be negative? It sounds like a mathematical cheat code.
It's not a cheat code, but it is heavily constrained. Quantum theory does allow for very limited negative energy effects in highly specific microenvironments.
Like what?
The most famous is the Casimir effect. If you place two uncharged conductive plates incredibly close together in a vacuum, quantum fluctuations outside the plates actually push them together.
Oh.
Yeah. The space between the plates effectively contains less energy than the standard vacuum of space, meaning its energy density is negative relative to the outside.
But that is on a microscopic quantum scale.
Exactly. There is zero physical evidence that negative energy exists as a massive, stable reservoir that could be mined or engineered to build Starship infrastructure. Mathematical permission does not equal technological feasibility.
Right.
You can write a structurally sound equation for a bridge made of a material that doesn't exist in our universe, but that doesn't mean you can build it.
Which forces us to look at how we traverse space without speculative shortcuts. Space is unimaginably huge.
It is.
Even nearby star systems are light years away, and general relativity strictly prohibits material objects from accelerating past the speed of light by ordinary means. So to travel, the story heavily relies on gravitational slingshots.
And gravitational slingshots are a real observed technique. A spacecraft approaches a moving astronomical body, like a planet or a star, and exchanges momentum with it.
Okay.
The spacecraft basically steals a tiny fraction of the planet's orbital energy to vastly increase its own speed. We use it routinely in our own solar system with probes like Voyager and Cassini.
But executing a slingshot around a gas giant is very different from plotting a trajectory near a supermassive black hole or a neutron star.
Immensely different. Plotting the mathematics of a slingshot trajectory is relatively straightforward. But executing it with finite thrust in a violently unpredictable gravitational environment, where any miscalculation of the ISCO or the tidal forces means instant destruction, that pushes the limits of material science and navigation.
Right. Now, all of this extreme gravity brings us to a massive, real-world triumph that occurred right around the time this story was being told. Kip Thorne, whose work anchors all of this science, was instrumental in the development of LIGO,
Yes.
the Laser Interferometer Gravitational Wave Observatory. And we finally detected gravitational waves. Did LIGO's success essentially prove all the wild physics in the movie?
It was a monumental achievement for physics, but we have to be specific about what the data actually confirmed. LIGO directly detected the ripples in spacetime caused by binary black hole mergers. It was. This greatly strengthened our understanding of black hole astrophysics. It proved that these extreme objects behave exactly as relativity predicts when they collide.
Oy.
But it absolutely did not confirm traversable wormholes.
Oh.
It did not confirm backward messaging through time, tesseracts, or any higher dimensional intervention. Those concepts remain entirely speculative storytelling devices.
But proving gravitational waves themselves was a massive leap.
Yeah.
And I want to address how we interact with that data, because people often hear the LIGO detections played as audio. It sounds like a quick chirp. Are gravitational waves just really loud sound waves traveling through the vacuum of space?
No, gravitational waves are not sound. Sound requires a physical medium like air or water to compress and expand.
Right.
Gravitational waves are actual distortions of the space-time geometry itself, propagating outward at the speed of light. As they pass through the Earth, they literally stretch and squeeze the physical distances between objects.
That is wild.
It is. The only reason we map the LIGO data into audio is to help human researchers analyze the frequency changes and communicate the findings to the public. It's a data translation, not an acoustic recording of space.
It's fascinating that we can measure a distortion in the fabric of reality that is smaller than a proton. But even with LIGO confirming these massive space-time ripples, general relativity is not the final word. It eventually breaks down.
It does. Classical relativity is fundamentally incomplete. When you follow the math deep inside a black hole, past the event horizon and down to the singularity, the equations just return infinities.
Right.
The classical description of smooth spacetime breaks down entirely under those extreme conditions of curvature and density.
The math essentially throws its hands up and says, I don't know what happens here, which points us toward the absolute unresolved frontier of modern physics.
It points us directly to the search for quantum gravity. We desperately need a theoretical framework that reconciles the continuous geometric curves of space-time and general relativity with the chunky, probabilistic rules of quantum mechanics. Because without quantum gravity, the absolute center of a black hole and the exact moment of the Big Bang remain profound mysteries.
And closely tied to that is the black hole information paradox, right?
Yes. There is a profound, unresolved tension between semi-classical gravity and quantum mechanics. Stephen Hawking showed that black holes aren't entirely black. They should eventually evaporate over trillions of years via Hawking radiation.
Okay.
But that radiation appears to be random thermal noise. This directly contradicts quantum unitarity, which is the fundamental rule that information about the quantum state of the universe cannot be permanently destroyed.
So if you drop an encyclopedia into a black hole And the black hole eventually evaporates away into random heat. Where'd the information in the encyclopedia go?
Exactly. Does the information escape in the radiation in a way we don't understand? Or does the universe actually allow information to be deleted? We just don't know.
Wow.
Furthermore, these extremes force us to question the fundamental laws of causality. The equations of relativity technically permit closed time-like curves.
That's right.
They're paths through space-time that loop back on themselves, essentially allowing time travel to the past.
Which introduces massive paradoxes.
It does. Physics currently operates under the assumption that the universe rigidly forbids closed time-like curves, perhaps through some unknown mechanism in quantum gravity that prevents them from forming.
Okay.
But until we have that unified theory, causality itself remains an open question at these extremes. These aren't just minor mathematical discrepancies, They challenge the absolute foundation of how reality operates.
It demonstrates that even our most rigorous, observed science inevitably leads us to the edge of the unknown, where we have to rely on models and speculation to guess what lies beyond. And before we conclude, I need to clearly state that this deep dive is an independent Cosmora HQ book overview. It is not an official or complete audiobook of Kip Thorne's work. We highly encourage you to pursue lawful access to the source material through the publisher, booksellers, libraries, or authorized digital services.
Yeah, the book goes into incredible depth regarding the specific equations and the interpretive models they built to bridge the gap between astrophysics and cinema. It is a masterclass in how scientists reason under pressure.
It truly is. It takes these abstract concepts of space-time geometry, time dilation, and extreme astrophysics, and forces us to confront our own limitations. I want to leave you, the listener, with something to mull over on your own as you look up at the night sky. Given everything we've explored today about the rigidity of general relativity, the demanding reality of extreme orbits, and the absolute limits of our observation, where should science draw the line between a possible universe and an imaginable one?